So I'm IQ from rgba, and even if there is no lot of people here now, I guess it's because it's Sunday morning, I'm going to explain the few people here about tricks and techniques for our intros, for the ones we made already and for the ones that are coming in future, hopefully. So this is a bit what I'm going to speak about. It's mainly 4 points. The most interesting one is probably the third and the fourth one, especially the third one, because the first and the second one are a bit more about what we already did, while the third one is about what we are going to do in future. So the first ones are just probably known things to everyone, but still I want to speak about them. So how do we do intros in rgba? So we don't have any demo tool or intro tool or anything like that as other groups. So we just have a 3ds Max exporter that exports single objects to text files, and that's it. The rest is done directly on Visual Studio by hard-coding in C, all the timing, all the scene graph, the objects, the textures, and so on. So it's really slow to do, but well. So we have Visual Studio, and we also have other tools like Photoshop or Messenger that are really handy for the development of the intros, because as you will see, the working pipeline is making use of these tools a lot. So everything is scripted in C, so it's not really scripted, it's just programmed. But well, when people is asking me, I like to say that everything is very nice script with a very powerful language that is C, because indeed it's very powerful. So that means textures are created with formulas. We don't even have a texture generator or anything like that. We don't base ourselves on layers and this kind of systems, but just we type formulas in C to create the textures. We will see it later. Shaders are also written directly on the C code. Well, it's ARB fragment programs, but still they are embedded on the C program inside a string with quotes and so on. It's not even text files out of the intro. Animations for meshes, it's also done in C. We don't have splines, we don't have anything. So everything that has to move has to be attached to a formula, and we have to move the objects or animate the characters by programming. Same for building the scenes or even generating the meshes. So the feedback is very slow, but still is nice because you just have to press F5, the thing is compiled, and you see it on the screen. So it's not that bad. So finally, you will see after the presentation that we like playing with formulas and mathematical formulas written in C. And we are suffering a bit like the matrix syndrome, on which you believe everything can be done with formulas. It's a very nice feeling. So what's the pros and the cons of not having a demo tool? So normally everything is bad, you know, not having a tool is making everything very slow, but I try to extract 5 points that are positive points. So one is that obviously you don't need to develop any tool, so you save a lot of time. Actually, I hate programming user interfaces, for example, so it would have taken a lot of time for me to develop even a single tool. So I just skipped all this programming time and all the bug fixing and so on. I didn't have to do anything. So I could use this time to make intros instead. So what else? Doing it directly in C is very flexible. So if you need something new for a new intro, or you need something special, you just program it. You don't have to make a new DLL, put it on your, you don't have to make a new plugin or change the code of the tool, adapt the user interface or anything. You just program what you need. If it works, it stays on the intro. If not, you remove it. But you don't lose time updating tools or anything. Another good thing is, at least for me, if I made a tool, I would like to reuse it across several intros, because for me at least, making a tool takes a lot of time. So then I would say, okay, now I have to use it for more than one intro. Then probably all these intros would look the same to each other because they are using the same system. So in my case, I can directly jump, if I wish, if I had the time, from one look to another very different looking intro, if I want it. So another bad and good thing is that, okay, everything is done in C, so you need a compiler, and artists don't like compilers. So that means that a coder is needed to make the intro. And that's nice because I had the feeling that in the last years, coders are just making tools and they don't participate on the intro. And that I like because finally I'm in the demo scene to make demos and intro. So I want to be part of the development. So because an artist cannot do it, I have to do it, and that's nice. So for example, in one of our first intros, Paradise, 100% of the textures were made by the coder, so by me. There was no artist involved at all. And in 70% of the 3D meshes, they were also made by the coder. So that's a big percentage of the content was created by the coder. So that's bad because it looks ugly, but it's good because I have some fun. And same for the cameras. So what's bad about not having demo tools? Well, obviously it's a pain to develop something and to have an intro working. So it's very slow. It's very frustrating because things don't look as they should, and you try to fix, and sometimes it's not easy. And the development is very, very slow. Well, you know the approach. You have a value somewhere that you want to change, so you change the value, you compile, you see the result doesn't look nice, you go back, you change, and so on and so on. It's very slow, but well, if you don't pretend to do 5 intros a year, but just one every 1 year or 2 years, then it's fine. You have the time, so why not? So how does it work? I already explained it a bit. So let's say you want to make a scene, you want to build a scene. So the coder starts building the scene. So it creates some procedural mountains. He creates randomly some rocks with spheres or whatever. And even there is a deer here, a mesh. So in the beginning, I didn't have the mesh, so I just placed a sphere instead. And I even developed the shader for the sphere, well, with the fur, for example. I had the shadows already with the sphere and so on. So I just prepared a bit how it should look like. Then I asked the artist to make the 3D mesh, and maybe 1 week after I had the mesh, I could put it inside. So then I got finally this with my procedural stuff and the deer. And I sent a screenshot to the artist saying, okay, look, this is what I have. So he said, oh, this is ugly because, well, it's empty. You need something more funny. So he took Photoshop, he took some pictures from Google and added some trees just in 2D to the image and sent it by mail to me saying, okay, let's try to make it look like this. So I said, okay, let's try. So because I didn't have any tool, I could very easily, quickly hard code some code to build trees, simple ones at least. So I had my trees, and I could send a screenshot again to the artist, and he said, okay, it's good enough. So we were done. So this is a bit the pipeline, but of course all this takes days or weeks because of course if you send an image to the artist, maybe he's not reading the mail at that moment, so maybe you have to wait 2 days, 3 days. It's very slow, but well. So for the cameras, it's exactly the same. Once the scene is more or less built, you have to make the cameras. And I normally make the cameras myself with sinus and cosinus formulas, for example, and just try to make a nice path. And then only if I'm not able to get a good path for the camera, only then I try to contact the artist and ask him to make something. Because making a camera with an artist is very slow, again. There is no feedback on the system, so what I have to do is to export the scene from the executable itself to a OBJ file format for 3D objects. It's a text file format. So he has all the bunch of polygons. He can import it in Maya or in Max. He makes the splines. He sends by mail again to me. Then I have to export the splines to TXT, convert that to an array of values, put it on the code, compile, see how it looks. And many times it doesn't look nice because there is some differences between Max and my camera system. So it's very slow. So I really try to avoid having an artist making the cameras for me. I always try to use formulas instead. So, for example, in Paradise, 3/4 of the cameras were made with formulas, and in our last intro, almost half of them were made with formulas. The others are made with splines by the artist. There is a problem, is that if you have some animated objects on the scene, obviously the OBJ file format cannot reflect that. So when the artist makes the camera, he has to make it with static objects. So if I have an object that in real time it will move like that, the artist has to blindly guess where the object will be and try to make the camera. So it's not very good, but well. So for the code, because we don't have any tool, we have to hard code everything on C. And this is a bit problematic because if you want good compression ratios, you have to arrange your data in very specific ways, like putting all the data of the same type together, whatever the origin is. So for example, putting all the floating point values together, whatever they mean colors or whatever they mean parameters or formulas. So in one hand, you should put all the types that are the same together, while in the other hand, if you want to edit something, you should organize your data according to what they represent. So you want a scene, specific scene to be in a CPP file, or you want the 3D meshes to be generated in another CPP file, but this is conflicting with the other data arrangement. So what we did is something in between. So we group data that is related together, but still then we split everything in arrays that have the same type of data. Well, so this is a small example. This is to create 3D meshes. So just an array of bytes. These are all defined to constants. So the first object is just made of 4 steps. One is loading a small mesh, then we apply a mapping, then we scale the object, then translate, and so on and so on. So all these commands here, like map or scale, they have some parameters, like the scale factor and so on. So this goes behind in another array of floats, for example, or in 16-bit value arrays. So they are close together, more or less, the parameters and the commands, but still in 2 different blocks. So that's the approach we took. So for the implementation of the 3D engine, for example, it's very simple what we do. We don't have a material system, we don't have lights, we just have meshes and shaders to attach to them. So the lighting is done individually for each object in each shader, according to, well, not according to anything, just we do it to make it look as nice as possible. So we don't even have a light that all the shaders are using, but we just hard code the dot products in each shader accordingly. So yeah, we also don't care too much about lighting models. So you learn about shaders, the first thing they show you is the Lambert shading model, the Fong shading model, well, whatever. We just don't care. So we don't even use the N.L, famous N.L diffuse term. We just use anything that looks nice. We sometimes do cross products between the virtual light position and the normal. We square it if it looks better. If it looks worse, we do a cube root, you say in English, power 1/3. Anything, so 1 minus multiply by the ambient occlusion term, or we subtract the ambient occlusion, whatever. So we just play until it looks nice. And this is done for each object. So even the shader between 2 objects that are close together in the scene, the shaders could be completely different. But well, who cares if it looks nice? So this is a problem if you are doing a game, because that means you have tons of shaders. And that's bad because you have to do a lot of state changes on OpenGL. But in intros or demos anyway, you just have a few objects, I don't know, 10 objects, 20 objects. So you are never going to suffer from state changes. So we can afford to have 1 shader for 1 object. So normally we have around 40, 50 shaders in each intro, but these are text, so they compress very well. So yeah, this is an example I wanted to show you about how to make textures, in this case, with formulas. So this is the texture we are going to create. I think it's I was a bit worried about the light because maybe you don't see it, but I think you can see it. So this is a texture we are going to create just with formulas. So the inputs to the formulas are the X and the Y coordinate of each pixel, of course, and the output is a color. Well, all these formulas are always resolution independent, so meaning the axis are scaled so that this is -1, the other side is +1, and so on in vertical. So we just use formulas, meaning sinus, cosinus, modulo, noise patterns, Perlin noise patterns, very useful, of course. Then we also use a lot step functions and smooth step to shape a bit the functions I will show later. We also have very powerful functions like the power or square root. This is used to adjust colors like contrast and these kind of things. And then you have other functions like exponentials and absolute values, very handy also. So let's say we want to do this butterfly. So how we do? Well, first we look to real pictures of butterflies, and we try to extract the main features of the pictures. For example, every butterfly is made of 2 wings. There is a ring of dark color on the border of the wings. You have some radial lines going from the body to the outside of the wings. Color patterns are always symmetric, and so on and so on. So this is what we are trying to synthesize with formulas. So we start with a basic shape with the formulas on the right. Well, who cares what they mean? It's just some functions in polar coordinates. I got the idea to make these formulas when I was at university making some, we were doing some exercises about antennas, radiation of antennas and so on. And we got some kind of formulas similar to this one, and the plots were looking like butterflies, and I said, okay, we can make butterflies with this kind of square sinus formulas. So everything is duplicated because I have one for the red and one for the yellow part. So the idea here is very simple. You just take every point and you have the radius or the distance to the center of the screen, and then every point that is close enough to the center, it's painted with a color. And this distance that is making the distinction between paint or not paint is just a function of the angle. So basically, these are the 2 thresholds for the distance, and with the step function here, we are really doing a comparison between the distance, the actual distance of the point with the threshold distance, and that step function will give 0 if one of the arguments is less than the other one, or 1 if it's the contrary. So then, by using this 0 and 1 to lerp or mix between 2 colors, you can get the appropriate color in each point of the screen. So next step, you can see the difference, is to, well, change a bit the shape so that it doesn't look so boring. And for that, you can see on the right in red the changes to the formulas. So we just had to add a small oscillation, high frequency oscillation with a small amplitude to make the shape move a bit. Next, I also wanted to, well, you will see the picture. I hope you can see it. There is here some spikes, I think it is. Sorry. And that was made by changing the profile of the yellow threshold with an exponential that, well, an exponential is just, it's always 0 except in a given point, normally in the origin, so you can translate it to a given point, so you can have a spike where you want, and by changing the the parameters of the exponential, you can do this shape to be wide or very sharp, and you can also change how big it is. So I just adjusted these values like 30 and 4p divided by 7, whatever, just to place the spikes in this position, not here. Or basically you can move them like that. Like you can make it longer or shorter, and you can make it thinner or thicker. So, wow, too fast. Yeah. So next, when the shape is done, next is add a bit of colors. I don't know if you can see it, but there is some orange colors on the top part. Well, that's just made by mixing between colors with some new formulas, like cosinus in this case. Then I added, this is interesting, I added a black border to the wings. I hope you can see it. So that was made by taking, again, the distance of each point and compare it with the threshold that I used to make the shape. So that's that division that is R divided by TH. So this value, it will be 0 here in the center of the screen, and it will be 1 just on the border. So if you made a plot of that, inside the wing you would have a kind of gradient going from the borders to the center. So, but that gradient is taking values 1 on the borders and 0 inside. So I wanted the contrary. I wanted to have 0 outside, so black outside of the wings and white inside. So I had to do 1 minus. You can see it just below. And then I have my gradient going from white to black in the borders, but I wanted to be the black part very thin. Like very thin. So I had my my color function, and I had to make power 64 to shape a bit the color to be a lot more like that, making a transition, very sharp transition. So then I got a black ring around the wings. So next step was adding these lines. And again, is made by using the angle and using a sinus based on the angle. So that makes kind of, I don't know, wavy color pattern in a circular way. I don't know. And then it's a matter of tweaking a bit this sinus so that the lines are not perfectly straight, but they bend a bit down, and well, and so on. Then you have again here a power. You see, everything is power 1 plus 40, whatever. That's again to adjust a bit the contrast of the lines. And then, well, a bit of Perlin noise to add some random details. And same for the lower part, the same idea. So finally, here it's not drawn the complete formula, but you can take all these small pieces and put them together, and you get the idea. It's a small C function with a lot of sinus and cosinus, but still just a few bytes. And okay, it's not a perfect butterfly. Maybe you could do it better with a texture generator. But well, it's very simple to do. You can do it once you are used to it, of course, you can do it in 5-10 minutes. So if you really know playing with the formulas and so on, it's really fast. So, well, that's the balance. You don't have to develop anything special. This is just C functions, but, well, you have a butterfly. So animations, they are done exactly the same. So, yeah, this is an example. This formula here is an example for the, if you have seen Paradise intro, there is some rhinocerons, I don't know in English, and they have the ears and they move them a bit like that randomly. So this is also done with formulas by taking every vertex of the mesh and moving it with a formula. In this case, it's a cosinus, so that the vertices do like that, but it's multiplied by an exponential to make a damping effect, so that they do like like that and they stop. And so that the ears they are not all the time doing like that. There is a noise function, Perlin noise function, that I use to trigger the movement of the ear. So when the Perlin noise takes a high value like 0.9, then I flag the animation on, and then the formula starts to affect the vertices. And then when the damping is high enough, then I put again the flag to 0. Then when the Perlin noise is high again, maybe 10 seconds later, the animation is triggered again. So what's good with this approach? Well, it's very fast to set up. You just have to find a formula and do it. There is no animator involved, so you don't have to wait for the artist to make a nice animation, and you don't have to wait for him to be inspired or anything. You just do it yourself, and you forget. Of course, yeah, it's a cheap animation. It looks like color animation, but, well, it's not that bad. Okay, this was a bit the demo system. I'm going to quickly go through some techniques we used, very simple techniques that people probably know, but still I want to share just in case. First one is ambient occlusion. You know, it's a lighting model. It comes from simplifying a lot the global illumination formulas. It's very simple to implement. I'm not going to explain it. You just Google for it. But what I want to say is that it's very simple to implement, very simple to understand, very quick to execute, and it's cheap to render. I mean, it's just one float that you have to use in your vertex, for example, and use it to modulate colors or to blend between colors or blend between textures or normal maps, whatever. It's really, really simple. There is no reason not to use it. I mean, well, you could say that all the demos using ambient occlusion, they look the same because they have the same lighting, but it's not true because all demos are using also diffuse lighting and they don't look the same. So you can do anything you want to with the ambient occlusion. It's not just about modulating your lighting. You can do blending of different things or whatever. So the only problem, at least in my implementation, because it was done per vertex, is that you need this is not the correct screenshot. Well, here I should have placed a screenshot with the wireframe of the mesh. So basically you need a lot of vertices on your mesh so that the ambient occlusion looks good enough. And it only works for static meshes because in my implementation I was pre-computing it. So more techniques, meshes. So you have to generate meshes, but at some point you also have to store meshes. So you can make procedurally a mountain, you can make industrial kind of objects like cylinders and so on, but you cannot make a human procedurally, or not at least completely. So, well, we only have two 3D mesh generators. It's a revolution objects and what I call seed mesh, is just a compressed mesh. So with revolution, you can do almost anything, from a box to a sphere to a cylinder to any revolution object. Yeah. And the rest is all about modifying these basic meshes with subdivisions, smoothing the objects, making them symmetrics, extruding, rotating, and this is the most important one, displace. It's a displacement of vertices, but again, this is a place where I can play a lot because it's not a hard-coded displacement. It's just a callback that I have, and then I can edit any formula I want again. So it's very powerful because I can create all kind of displacement just by editing formulas. I will show some examples later. Well, yeah, these are the examples. So on the left, top left, you have 2 columns. These are revolution objects, so they are made of 5 or 6 points. Then these points are revolved to create the surface. And then the trick to go to the right image that is a bit more detailed is to just a displacement and hard code some sinus formula. So you just take, if this is the column, you just take for each point the angle it makes compared to the axis of the column, and you just apply a sinus to the vertices and displace them on the normal direction with the sinus. And then you get that detail on the right. That is good. Then this is another example also of using cosinus. So the body of the guy here, this green part, is made of, I don't know, 6, 7 polygons. Then you subdivide it, you have a smooth shape. And then, well, it was looking too smooth, and in the original demo, we wanted to replicate. The guy had some these shapes, I don't know how to call it, waves or ripples. It was like that. So we had to create this from the smooth surface we had by displacing the vertices with some cosinus again, in this case. So displacement with formulas are really useful. This is another example. This object on the right is made from this mesh on the left. So it's a planar mesh, 2D mesh. We just we make it symmetric, then we extrude it to give it a bit of a depth. Then we subdivide so that the square profiles gets rounded and so on. And then you have a kind of wheel. And then we had to grow the teeth, or I don't know, we had to grow these things on the profile. So we used again a displacement and with a small formula, again with a cosinus. And well, we got this shape just from a few polygons. But at some point you have to store 3D meshes, not only generate but store. So normally the first thing we made in Paradise was a very simple compression method, and we used only 200 polygons for each object. Then we improved it a bit, and we could go up to almost 1,000 polygons per object, and still at a reasonable amount of data on the demo. So if you ever try to compress a mesh, you will probably know that the problematic part is the vertices. So the indices of a mesh, so the connectivity of the vertices, that's very cheap. It compresses very well. I guess it's because it's integers and so on. But so the vertices are the big problem. And if you have a look to the research papers about mesh compression and so on, you will see that they speak about fantastic compression ratios, like 1 bit per face or per triangle. But in reality, in intros, we will never arrive to these values of compression, this amount of compression, mainly because these papers that they always work with huge meshes, highly tessellated meshes also. So, I mean, every triangle is very coplanar with the next triangles around. So they can use a lot of tricks like prediction of vertices and so on, and that works very well. But in our case, the meshes are everything but smooth. So when you have this object that then is subdivided to this one on the left, okay, this is, I don't know, 800 polygons, but each vertex is quite different to the neighboring vertices. You cannot really predict too much of one vertex knowing the others. So it's a bit like a noisy mesh. So we have to do something else. We cannot just apply what they speak about on the papers. Well, I will go a bit later for compression, but first, of course, not everything is just generate and compress. You can use other tricks. Like, for example, the guy on the left, these wings, they are symmetric, so you only have to store one, of course. The other one is just mirrored to the other side. Then you have the B on the center of the screen. Again, the legs are all the same, so the green parts, you only have to store one of those, and then make 5 copies, and the same for the brown ones. Then the body, the blue one, is symmetric, so you only have to store half the mesh. Another interesting one is the one on the right. So you have the head of this guy, and you see from this picture that the head is not symmetric because he has two, wow, how to call these things? Horns, is it? So you have two of them, each one is bended in one direction. So, okay, it's not a symmetric mesh. You cannot just store one half. You have to store the complete thing. But no, what we did instead is that we modeled the head with these horns not bended, but straight. So the mesh was symmetric. So that's what we stored, sorry. Then we made a symmetric copy of it. And then we used a displacement shader again to bend manually in code with some cosinus to bend the horns to break the symmetry. So there is many things you can do before trying to compress in brute force everything. Okay, so, wow, time goes fast. Future, what we are trying to do, well, what we already did, and we will use, hopefully, in next productions. So we were trying to find a better compression method for 3D meshes. So as you know, the first thing you have to do to compress a mesh, to store a mesh, is to quantify it. So you don't store the vertices in floating point values as usual, but you just take the bounding box of the object, you normalize all the vertex values to 0, 1, and then you rescale to 0 to 155, for example, if you want to fit everything in bytes and not in short values. So first trick is to use less bits on the dimensions of the object that need less precision. So this dimension is very long, so you better subdivide it in a lot of slots, or I don't know, for example, in 256 steps, while this other dimension is a lot shorter. So it's useless to have 256 divisions here. You just need maybe 32 or 16. So the first thing is to use less bits on the dimensions that are shorter. Yeah, next thing, this is a nice one also, I think. So we didn't use it yet, but I think it's a good idea. Well, it is a good idea to split your meshes in parts. So this part of the mesh on the left, and you can see different colors. And so this is a mesh, this is another one. Then you have the head, you have the neck, and so on. So each one is a different mesh. And what's the point of this? Well, the point is that, for example, on the head, you want a more you want a lot more detail than on the body. Okay, so if you add this character to an intro, everybody will look to the face more than the, I don't know, other parts. So you really want detail on the face. So if you split the mesh on the head, you could compress that part, those vertices, with a lot more bits than the body, where you don't care to lose a bit of precision because the body is not so detailed anyway. Probably there is some cloths on top of it. So that's a good trick. Of course, you have to develop something to join meshes at runtime, but that's very simple to do. Just few lines to compare each vertex position with every other vertex on the other mesh. You take the two closest and you just merge them, and you are done basically. So this is a good thing, and it also has some good side effects that we will see later. So how to store the vertices? So you first quantify them, and you store them as bytes, for example. And then you do delta coding on those, because normally, even if we said that the meshes are quite random and noisy, there is still some coherence between vertex to vertex. So you can still do delta coding and get some improvement compared to brute force storage. It's also a good idea to store the X, Y, and Z components of the vertices in different arrays. The same for the texture coordinates. For indices, so for the connectivity, also the same. You just use indices and you delta encode. So, well, this is a bit up to the Max converter or Maya converter. It's up to it to do a good, how to say, good traversal of the mesh, so that the polygons are exported in a way that you don't jump from one place of the mesh to another. Because if you just export the triangles one by one, going from one polygon to the next one that is connected to the first one, then your indices, if you do delta coding on them, you will have very small values. While if you just jump from one place of the mesh to another, the indices will be random, and the deltas are everything but small. So it's not perfect, this system, but it works more or less well. But yeah, so first problem is you are relying on the converter to make a coherent traversal of the mesh, and index arrays could be compressed a lot better. So this is the system we are using now. It's we just export all the mesh from max, and then we re-export it somehow, and we do a traversal on the mesh that we can control. So for example, what we do is just a depth first traversal on the mesh. So for each polygon, we just compress, compress the neighboring polygons, and for each one, again, the neighborings, and so on and so on. So the trick is that once you have, let's say you are in the first step and you have the black quad already converted, you want to convert the blue one. Well, you want to export or compress the blue one. Well, you have to give the two new vertices in blue, and you also have to give connectivity for two new additional vertices. While normally you should need 4 values to specify the new quadrilateral. You need to give which 4 vertices are connected to make this polygon. But here, because you know how you are traversing the mesh, you only need to give 2 new indices. So you basically save half the index array data. And the good thing is that you are really traversing the mesh in a coherent way. So you are not jumping from one vertex to another. And this allows for the second point here. You can do a lot better prediction than just delta coding. So let's say you already exported these 3 vertices. You are going to export a new one here, D. So what you could try to do, instead of just delta encode D from C, that it was the last exported vertex, you could try to predict where D would be. So in this case, I used a very simple predictor. It's this one here. So basically, it's taking this edge and moving it to C, and it gives the new vertex position. So this is just a prediction where the vertex could be. It's not here, of course, it's here. But now you only have to encode this error you made on the prediction. And this is more value compared to the delta that you would store otherwise. So this helps a lot also. It's a nice thing. So we said we were going to split the meshes in parts to have better to have better control on the precision, and this allows for very nice tricks. For example, I call it Collagen. I don't know if you can say that in English. I think it's a French word. It means that you can have a collection of heads, a collection of bodies. Well, not even heads. You could have a collection of noses and ears, like 2 meshes, 2 different meshes for the nose, 2 different versions of a nose, 2 different versions of a mouth, and so on. And then, because you can just attach objects to each other, you could make, 10 different faces just from 4 meshes. So if you combine the 2 noses you have with the 2 heads and the 2 ears and the 2 bodies, you can, all these combinations give you, 16 different meshes, and you are doing it from really a small amount of pieces. Of course, it's not only about having 2 noses, but if you have 2 noses, you can blend these meshes, and you have all the intermediate noses. You can make a lot of variations just from few base meshes by this Collagen technique. This point, very powerful in combination with delta meshes. This is for storing. So let's say you decide to store this mesh, the head here, the face, and now if you have another face that is slightly different, let's say you made it by just deforming this one here. So you keep the topology, you keep the index arrays, you don't remove or add polygons, you just move a bit the vertices. Okay, now if you want to store this second mesh, you don't have to store it from scratch. You can just store what's the difference between the new mesh and the original one you used to create the new one. So you could just give for each vertex how much it was moved to create the new mesh. And this is, again, very small values. So once you have one mesh converted or saved or exported, compressed, next ones can come for cheaper amount of data. More techniques. Well, I guess next step on intros is to have animated characters, probably humans, because we care more about humans than animals. So we need a skeletal animation for that, and that means we need, for each vertex on the mesh, we need a weight, you say, an influence for each bone of the skeleton. So each vertex has to be attached to one or more bones with a given weight. So all that, you normally should export it from Max or Maya and so on, but that's a lot of data to store. So instead, we try to generate these weights algorithmically. So for that, I have to go fast. For each vertex, so well, inside here, you have to imagine there is a skeleton. It's a very simple one made of 20 bones. So for each vertex, we just do point to line segment distance calculation. So for each vertex, we know which are the 4 closest bones, and based on the distance, we can assign some weights. And then here I used a color to show to which bone each vertex is attached. Well, what is the first bone to which it is attached? So you can see this part, all these vertices are attached to this bone here, these vertices to this one, and so on and so on. So if you just use these weights to do animation, it looks a bit crappy. I will show an image later. So the trick is to blur this information. So you have the values for each vertex. You just look to the neighboring vertices and you blur the data a bit by blending them together. And that's how it looks on the left. And this is a lot better weight for the animation. So on the left is just using the closest bones, and you have these artifacts, as you can see here, and also here in this part. It's very straight. While if you just blur a bit all these values, you get the image on the right. That is quite better. And it's good enough to do some animations, and you save a lot of data. This I'm going to skip. Okay, so what else will come next years in intros? Cloth simulation, probably. Well, at least I would like to see that from the technical point of view. But cloth is not easy. So here I just picked some images from the internet about CG movies, and you see there is no clothes on it almost. So everything is about animals, cars, robots, toys, whatever. There is no cloth. It means it's very difficult to do it. Even if these people in Hollywood cannot do it, how would we do it in real time, no? And in 64Ks. So, well, there is some cloth here, but it's really attached to the body. It doesn't move with physics or anything. And in Rec, the cloth is quite crappy, I think. So this is difficult to do, but still, we should try. We are demo sceners, right? So we have to try crazy things. So how? Well, we use the classical spring mass approach. You probably know it. There is a lot of demos on the internet with just a quad with vertices, and it moves like a cloth. So it's based on giving to each vertex of the mesh a weight, a real physical weight in kilograms or grams or whatever. And then each edge is simulated with a spring. And you apply some basic physics, not even differential equations or anything, just simple physics like update the position of each vertex with a velocity, and you update this velocity with an acceleration that is normally gravity. You can also do a bit of friction and so on. So, yeah, but there is a problem. You need collisions because you don't want the cloth to traverse the body. So if you put, if you have this mesh here and you want it to become a cloth, you want it to stay on the body. You don't want to fall that it falls down. So you need to collide the mesh, the cloth mesh, with the body mesh. So, well, first, of course, well, this is a bit idea. So you only have to store this mesh, simple mesh, the blue one. It's 20 polygons or 30 polygons. Then you subdivide it, and it gives you a kind of ugly cloth. And then you apply the physics, the mass spring model, and you get the images on the right. I think I have a video, but maybe I can show it after the 45 minutes if somebody wants, because otherwise I will lose too much time. So this is another example. So you just have to store this stupid mesh here. You subdivide it, you apply the physics, and you get the one on the right. It is, well, it's not perfect, but it's something. Good news, here you have to do collision detection. Normally it's very slow because you have to collide each vertex of the cloth with a complete mesh. And because it's 64K, I didn't have any CADE tree or OC tree to accelerate this. I just do it in brute force. But because our mesh is made of small parts like the head, the body, and so on, I can just pick the ones I need for the collision. For example, if I'm simulating this, I don't need to collide all these vertices with the head. So I just pick the pieces of the body that I need, like the legs and so on, and I just use those parts for the collision detection. So what about real-time clothing? Because this is just static, you do it, it's very slow. So you can do real-time cloth simulation if you could quickly collide your vertices with the mesh. As I said, normally if you had a CADE tree, you could do it in real time. You can cast millions of rays per second with a CADE tree. But it's 64K and the character is moving, so you should recompute the CADE tree every frame. This is slow. So instead, I use some spheres. So it's a very old model, but well, still, you have to imagine the skeleton here, and the red points the red spheres are the joints between the bones. So you only have to add one float for each bone, saying how thick it is, how big the radius is. And all the blue spheres are then just interpolated and created in real time by interpolating this radius across the bones. And then you can use these spheres to do real-time collision detection, because raycasting on a few spheres is very fast. You can do it and it works well. It works more or less well. The image on the right is a real-time image. I'm not going to show it. So what else? Hair. This is also something difficult to do, according to what I see on the movies. There's only one character here that has real-time simulation of hair. Is this one here in The Incredibles, the girl. All other ones, they don't have hair. They are bald. They are animals, cars. Or in this case, they have hair, but it's really blocky. I mean, it moves like a solid with the head. There is no simulations on that. So that's the next step. I don't have pictures to show it. I didn't have the time to take few. But I think we will see this in future. Okay, so last points. I think we still have the time probably. So tip and tricks. This is more for programmers. Well, everything was for programmers, but this even more. So this is very simple thing. Still, I don't see people doing correctly, I think. So I'm going to jump to this one. How to normalize a mesh. So when I see code on the internet, people is doing very complex things like taking each triangle, calculating the normal to the triangle, and then for each vertex, finding which triangles are connected to this vertex, taking the average, adding up together all these normals of these faces, dividing by the amount of faces, and all these complex things. But it can be done a lot easier just with these lines of code. If you realize a few things that are written here, I have to go quickly, so I'm not going to explain. But basically, for example, you don't have to divide by the number of faces, because you are going to normalize the vector anyway, and this division is only changing the length. So who cares to do the division, and so who cares about keeping track of this value? You just remove that code. You also don't have to do the normal for each face, because if you have this triangle on the right, top right, and you do the cross product on the left, the normal usual cross product to get your normal, and you expand it, you will see that it's made of 3 sub-dot products, one for each edge of the mesh. So instead of just calculating the normal for each face and then accumulating, you could do directly calculating these dot products on the fly and accumulating them on the final vertex normal. Well, it's a trick, but finally you can do this. Something else is that you see there is no square root. You normally do square roots to normalize your face normals and so on and so on, but you don't need it, because normally normally not always the cross products, the length of the vector that comes from the cross product, the length is proportional to the triangle. So the bigger the triangle is created by the two edges, the bigger the normal. So that's good, because that means that these normals coming from big triangles will influence more on the final normal than the small triangles. That's something good. So if you have very big face for this table here, and then you have these small triangles here, the vertex normal, if you had to do a vertex normal here, would probably more likely be more vertical than horizontal. So that means this horizontal triangle that was bigger had more influence on the vertex. So, and that you can just do it by removing the square root. So perfect, it's faster, it's better. You can use it in real time to renormalize meshes if they are moving or deforming. Something else very quickly, this I'm not going to explain it, but basically you can do Catmull-Clark subdivision. That is the subdivision schema we use. You can do it just 30 lines of code here, 50. When I see implementations on the net, you very quickly arrive to code that is 2 CPPs where I don't know, with 1,000 lines and so on, because they build edge trees and very complex data structures. But you don't need it if you just rearrange rearrange the operations and you just iterate on the faces and so on. Well, you can arrive to this kind of code. I will put it somewhere on the net if somebody wants to have a look. But basically, it fits in 400 bytes. So you can even use it in 4K intros. So what's the future, I think? We will see cloud simulation, hair, real-time collision detection, physics, global illumination probably, and so on and so on. Well, that's what I would like to see. I don't think there is technical problems to go for it. Well, we need the time to develop all these, of course, but I think it can fit very well in 64K. The big problem is that you need an artist to give you data for all this. I mean, you cannot do character animation if you don't have a skeleton. You cannot do it if you don't have a mesh, and so on and so on. So for me, there is a problem here because you need, well, artists will be more and more involved on intros. That's very nice because they have good taste for colors and so on. But that's bad because you depend on them. It takes time for them to do all these things, and they have to do more and more things. So before, 5 years ago, by just making boxes and cylinders, everyone was happy. Now you expect a lot more, and if you expect skeletal animation, you need a skeleton. So it has to do it, and not all artists can do it well enough. So they also have to improve, and the artist will become probably the bottleneck in future for 64K intros, I think. So the mandatory question mark, if you have any question. Well, let's see if I can understand, because my English is not so good. So speak slowly and I will try to catch it.
Yeah, actually I have two questions. The one is about that artist you were talking about as well. You showed this mesh of this, polygon mesh of this dancer. And I guess you did this subdividing stuff in the code and not in the Maya or Max. So how does it really work? Because the artist cannot really see the resulting model when he's modeling the polygons. Yeah,
well, what we do is that he just uses the subdivision that it's implemented in Max. So we assume my code is similar enough to the Max code. And so he works with the Max modifiers. So when he has to symmetrize a mesh, he uses the Max symmetry stuff. Then he subdivides with Maya, Max, sorry. And then he hopes that my code is similar enough. Yeah.
Okay. And the other one was with these collations, or with these where you split the part in different sub-meshes. That with noses you can attach several different noses. But can you really attach different noses, or because I think where they
have to share the boundary.
Yeah, and the same amount of vertices as well, and
yeah.
Okay.
Well, no, not really. The same amount of vertices on the boundary.
Yeah, okay.
Yeah, and the boundary cannot change, of course. It has to be the same so that they connect correctly. Yeah.
And you really encouraged me to start coding now straight away and go away from worrying about which tools I have to make for the artists. But don't you come to the point often where you say, I've written this code thousands times, or you start developing the same stuff over and over again? Or do you have libraries which you use for, let's say, if you create a texture from a formula, you have all this code who will actually create it, and just 3 lines for this formula. So do you write this code which actually creates the whole shader? Do you write it over and over again, or do you have a shader where you just paste your formula, basically?
Well, for textures, you cannot reuse anything because each formula is different. So there is nothing to reuse there. On shaders, I said I have 50 shaders, for example, but they are all more or less similar. Finally, you just copy and paste many things. For the rest, for the 3D meshes, well, there is, as you saw, there is very few functions that you need, like symmetrize or make symmetric objects, subdivide, and this is small function. So these are reused, of course. Some of them are coming from the 98 when I made my first intro. So, but what I like is that most of these algorithms are very useful, but are very small. The subdivision one is the longest one; it's 50 lines. But the others connecting to meshes is just a double loop. It's something like that. It fits in a page down. Symmetrizing an object is also looping on the vertices and making a copy if they are close enough to the symmetry plane. So it's very simple algorithm, and it's very. With very few work, you can get many nice things.
Okay, thank you.
Okay. So finish.